Good afternoon and welcome to my presentation about our evaluation of neural network architectures for the task of sonar echo classification in air. My name is Kroh, and me and my colleagues are from the University of Erlangen-Nürnberg. There we teach and conduct research in the area of sensor technology. I hope you will enjoy the lecture and that I can spark your interest for the topic. Apart from myself, Kroh, this work has been co-developed and implemented by Mrochen and was supervised by Stefan Rupitsch. For current mobile robot navigation, laser scanners and cameras are used predominantly. The tasks include mapping and localization, as well as the combination of both, which is called SLAM. The mentioned systems can be confused by shiny and transparent objects, such as glass doors or stainless steel surfaces, which can be found in various environments. These include hospitals, office buildings, as well as factories, for example. In such settings, ultrasonic sensors can serve as a valuable addition to a robot sensor setup, as they are impervious to the aforementioned optical obstacle attributes. In addition to merely detecting an object's presence, it is also possible to obtain further information about an object from its ultrasonic echoes. Such information is especially interesting for current semantic graph SLAM approaches, in which scenes need to be recognized by distinctive features so that successful loop closures can happen. As a consequence, we focus on the development of a suitable ultrasonic sensor system in our general work and present our findings about possible classification models in this lecture. I started with the main motivation for our work and will now go on with an explanation of its underlying concepts. After that, I will present to you the network architectures that we have investigated and the results that we obtained with these, which will also be discussed. The last section will be a conclusion with an outlook to ongoing research. Let's begin by assuming a robot equipped with an ultrasonic speaker and microphone, which moves in an environment with obstacles. It repeatedly emits sound pulses, which propagate through the air, are reflected by objects, and whose echoes are then recorded, pre-processed, as well as classified. We use rectified narrowband downtrip signals for electrical excitation of the speakers. The frequency range is determined by the usually available bandwidth of piezoelectric transducers, which are the standard for most of today's common robotic applications due to their robustness. Prior to classification, the recorded echoes are pre-processed. The pre-processing comprises peak detection, region of interest selection, and feature extraction. Peak detection is based on pulse compression with cross-correlation of a previously recorded reference signal. Regions of interest are selected so that classification is only performed on relevant signal parts, as well as to reduce the amount of necessary computations. And the feature is any kind of refined information that is relevant for the classification task. For our system, we chose to use an estimate of an object's target strength, the echo delay, as well as a spectrogram of its echo. The whole pre-processing is executed for 3 subsequent echoes from the same object. The produced data is aggregated, and the resulting sequences are input to the classifiers. Traditionally, ultrasonic targets have been divided into 3 principal categories in related publications. These are generally walls, edges, and corners. Yet, there are many real-world objects whose shape cannot be described by such forms, as they exhibit curved surfaces. Examples include round objects, such as table legs, plant pots, and waste paper baskets. As a consequence, we chose to generalize aforementioned classes into flat, convex, and concave shapes. For datasets, we then decided to use disks, spheres, and hollow hemispheres as target primitives, since these are the most generic fundamental three-dimensional objects of the discussed shapes. In order to achieve size-independent shape classification, we employed multiple, differently sized objects. Datasets are required for training and testing classifiers. As there exist no reference datasets of ultrasonic echoes for the presented application, we had to create our own. For that purpose, a test setup has been built, which consists of 2 translation stages, a rotation stage, as well as mounts for the target objects and ultrasonic transducers. With the setup, it is possible to recreate a robot's path by an obstacle in a repeatable way with a reliable ground truth. About 3000 sequences of adequate echoes could be obtained. It is now time to go on with investigated network architectures, as the main concepts have been discussed. The general structure of artificial neural networks is depicted in the upper left part of the slide. There is an input layer, a set of so-called hidden layers, and a final output layer with one artificial neuron per classification label. The first network type here is a simple multi-layer perceptron. It is a kind of network that consists of multiple layers of neurons, which are fully interconnected between the layers and are also called dense layers for that reason. What happens inside a neuron is that all the input connections are weighted, summed up, and the sum is given as input to a nonlinear function, which is called activation function. The weights are the parameters which are actually learned. The best structures that we have obtained are given in the lower parts of the slides. The next network type is a convolutional neural network. Here, convolution layers are added, which are often also combined with so-called pooling layers. By this, much deeper structures than with multilayer perceptrons are often possible, which has also led to the term of deep learning. In a convolution layer, a discrete convolution is performed on the input data with a filter kernel, whose weights are the actually learned values. The third investigated network type is capsule networks. Such networks incorporate layers of so-called capsules. These are entities that comprise multiple neurons and to which data is fed in the form of multidimensional vectors. This often leads to more detailed modeling of features and their interrelations in contrast to convolutional neural networks. As an example, capsule networks have become famous for good modeling of pose relations of parts of an image, which is something that is quite hard for traditional neural networks. Another basic neural network type is long short-term memory networks. Such networks have got internal variables that enable them to store an internal state which can persist between subsequent network executions. What is actually learned are the weights of the internal neurons, which are also called gates here, and whose number of weights is independent from the number of input sequence objects. Due to this property, LSTM networks are capable of processing sequential data regardless of the number of contained sequence elements. This can be especially beneficial for classification performance in our application if more and more echoes from an object become available, which we have shown in our referenced literature. The last architecture that I want to discuss is modular neural networks. In contrast to the previously discussed network types, modular networks do not just consist of sequential combinations of various different layers, but also incorporate parallelly running branches. For our application, we have created a modular network with two input branches, which we call SplitNet here. The architecture gives the network the ability to individually process input features with respect to their individual shape and information content. In our case, the CapsNet branch is responsible for processing 2D information of a spectrogram feature, and the LSTM branch handles the scalar input features, which are target strength and echo delay. The results that we have obtained with this architecture, as well as with the others, will be shown on the next slide. Various performance values have been investigated, of which accuracy, inferencing time, and confusion matrices are shown here. Accuracy denotes the ratio between correctly classified and available samples in our test sets, which consists of 15% of the total amount of samples. Inferencing time is the duration that is required by a network to predict a class, and a confusion matrix is a table that shows relations between actual network input classes and predicted output classes. It can be deduced from the graphs that all networks may be used for classification and that the best performance is apparent for the SplitNet at the cost of the highest inferencing time in the comparison. More detailed results can be extracted from the confusion matrices. Confusion mainly appears to be in relation to disks for most networks, except for the SplitNet. It appears that individual strengths of the underlying basic networks could be combined in this case. In summary, I have shown you an evaluation of a couple of neural network architectures for echo classification with respect to constraints which are usually present in mobile robotic applications. Our results show that all the investigated architectures may be used for classification on an embedded platform, as the inferencing times are fairly short, at less than a millisecond on our test platform. Also, a trade-off between classification accuracy and computational effort is possible to find a suitable solution if hardware restrictions are given. And, as a final conclusion, by use of modular architectures, it is possible to combine strengths of individual basic networks and adjust the processing with respect to the input features so that best results can be achieved. As an outlook, I want to give you a little insight into our current work, which is also motivated by the findings which I have presented in this lecture. We have just finished building a custom sonar ring and equipped the robot with it for practical real-world data acquisition, for which we also refine and optimize our classification models. In addition, for real-world deployment, integration of our sensor system with SLAM is also a major task which we are focusing on. On this slide, you can see the main references for the lecture, including our own previous work and the most important literature for understanding the basic concepts behind the work. Thank you very much for attending my lecture. I'm looking forward to discussing your questions.